chemistry. This is lesson 2, discovering the atom. We're going to pick up where we left off with the basic atom lecture and learn more about how atoms are structured and what they are. So an orbital, also called a shell, is an energy level at which electrons must stay. Electrons can pass from one orbital to another but cannot stay in between orbitals. So Niels Bohr came up with the idea of circular orbitals about 100 years ago. You will learn later that the shape of the orbitals is more complex than this. Electrons in orbitals further from the nucleus have more energy. Orbitals can be compared to steps on a ladder. You can climb up or down steps on a ladder, but you can't stand in between steps on a ladder. You either have to be on the higher step or the lower step. You can't stand in between them. In 1897, English physicist J.J. Thomson discovered the electron. Thomson placed a negative plate and a positive plate at opposite ends of a cathode ray tube, which caused a stream of electrons to move across the tube. So the electrons are negatively charged, so they're going to move away from the negative plate, and they're attracted to positive, so they're going to move toward the positive plate. By placing a magnet on the side of the tube, he caused the electrons to curve. So electrical charge, which we're interested in chemistry, and magnetic charge are related. Magnetic charges can cause a movement of electrons or of protons even with electrical charge. So the two are related, but they're not exactly the same thing. He was able to determine the mass and charge on an electron. So there you see a negatively charged plate. That's called the cathode, and that repels electrons because negative repels negative. Over on the right, you have a positively charged plate called an anode. That attracts electrons because positive attracts negative. Now that's an actual picture down there of a stream of electrons. You can't see one electron, they're too small, but if you have a very, very, very large number of them, you can actually see that stream there. So this creates a visible stream of electrons. And over on the right, lower right, a magnet causes the negative electrons to change direction. So that's again is an actual picture. In 1904, Thomson proposed a model of the atom that included electrons. He knew that there must be a positive charge to balance the negative charge of the electron. He believed that the positive charge was evenly distributed in a sphere with the electrons spread around the sphere. So if you see that pink image right there, he thought there was just this general, you can think of it as a big ball of positive charge. The positive charge was in no particular place. It was just spread out throughout that big ball. And stuck in it were these little electrons. They were just kind of stuck inside of it. This became known as the Plum pudding model of the atom because it was a soft, solid sphere with chunks of electrons. So there's English plum pudding. It's not what we think of as pudding in the United States. It's more like kind of a bready, kind of a cake almost like a muffin in a way. So he thought of it that just like as you have chunks of plum stuck in that plum pudding, you had chunks of electrons stuck into the positive sphere. In 1911, Ernest Rutherford performed the gold foil experiment. The experiment demonstrated two things. One, an atom has a solid nucleus center, but that most of the atom is empty space. Rutherford shot alpha particles, which are positively charged particles that contain 2 protons and 2 neutrons, at a thin sheet of gold foil. If Thomson had been correct, the alpha particles would have shown a small deflection, because that sheet of gold would have been essentially one continuous positive charge, and these alpha particles would have just kind of gone through it. In fact, most showed no deflection, and some actually bounced back. This indicated that that there was a solid nucleus surrounded by empty space. So here's kind of a expanded view animation of this. So there you have alpha particles. Those are the little orangish dots that are going through, and they're being shot through a through the gold foil. So you notice that several of them just pass straight through. They don't change direction. They don't do anything. If one of them comes close to the nucleus of gold, then it actually curves, because the protons inside the nucleus of gold will repel the protons in the alpha particle and cause it to curve away. It'll kind of push it away. But every once in a while, one of those alpha particles is going to hit dead on, just hit straight on to that nucleus, and it's going to bounce back. So most alpha particles miss the nucleus. Some are deflected by the positive gold nucleus, and a few hit directly and bounce back. So that told Rutherford that most of the atom must be empty space. If the alpha particles don't bend at all in some way, as a positive particle going through a positive solid should, then it tells them that the positive is not spread out throughout the gold foil. But a few of them actually bounce back, so that indicated that positive charge must be concentrated in a solid nucleus to cause some of them to actually bounce backward. The discovery of the proton is credited to Ernest Rutherford, who proved that the nucleus of the hydrogen atom, i.e. a proton, is present in the nuclei of all other atoms in 1917. In 1932, English physicist James Chadwick discovered a particle that had the same mass as a proton but no electrical charge. This particle was called the neutron. So the neutron was discovered less than 100 years ago. Much of what we've learned about chemistry has happened in the last 80 to 100 years. Protons and neutrons each weigh about 1,820 times more than an electron. So if you put the nucleus of a helium atom floating above the middle of what used to be called San Diego Stadium, what used to be San Diego Stadium, and the stadium were the atom, the nucleus would be about 1 millimeter in diameter. The electrons would be in the upper level, and most of the volume of an atom is empty space. So if that's the nucleus right there, represented by the 2 neutrons and 2 protons, it wouldn't even be visible from where you are in the stands right there. It would be 1 millimeter, so tiny you wouldn't even be able to see it from where you're viewing that. But it would be located right above the middle of the field, and the electrons would be way out, way up in the upper deck or outside of it. So you can see that most of that would be empty space in between the electrons and the nucleus. An isotope is an atom of the same element but with a different number of neutrons. So this is a lithium-7 atom, and you're going to learn how to diagram an atom in just a few lessons. A lithium-7 atom has 4 neutrons. So the 7 means that it has 3 protons and 4 neutrons. It also has 3 electrons. It has to have the same number of negative charges, electrons, as positive charges, protons. But we're not interested in those right now for this part of the lesson. There's another lithium atom. It has 3 protons. Remember, the number of protons defines the element. Lithium must have 3 protons. It also has 3 electrons, but what you'll notice is it only has 3 neutrons. So that's called an isotope. It's the same number of protons, same number of electrons, but different number of neutrons. What effect does that have? It doesn't make the 2 atoms any different than each other in terms of the way they react chemically, but the lithium-7 atom is heavier than the lithium-6 atom because it has 1 more neutron, and that does have some effects on chemical reactions at certain times. So the notation for an isotope this is the isotope notation, is the mass number is on the top. That's the total number of protons and neutrons added together. If you remember, each proton and each neutron has a mass of 1. We said that in the previous lesson. So if you have 3 protons and 4 neutrons, the lithium on the left, that's a total of 7. So that's the mass number, total number of protons and neutrons. Each one has a mass of one atomic mass unit. So that means its mass, basically its weight, is going to be 7. The electrons don't count. They are considered to not have any weight, even though they really do. They're just considered to not have any weight. The atomic number, and we're going to learn about this very shortly, is the number of protons. So lithium must have an atomic number of 3 or it's not lithium. So it has 3 protons. The mass number, the mass of a specific isotope, is on the top of the atomic number, and the atomic number is on the bottom. So that's the way you would write an isotope. We very rarely use this notation because we're generally not interested in isotopes at the level of chemistry we're learning. This is more significant when you get into nuclear reactions and need to keep track of protons and neutrons in the nucleus, because that will change in a nuclear reaction. So an alternate notation for an isotope is this. This is exactly the same thing as the last slide. So Li7. So that means it has 7 protons and neutrons, or a total mass number of 7. You don't show the atomic number because it's assumed you know that if it's lithium, it must have an atomic number of 3. That means it must have 3 protons. It wouldn't be lithium if it didn't have 3 protons. So in this notation, you only show the mass number. And same for the one on the right. You show the number of protons and neutrons. Another way an isotope can be expressed is shown here. The atomic symbol is followed by the mass number. An ion of an element is an atom that has a different number of electrons than protons. So here we see an electrically neutral, a normal lithium atom. It has 3 protons, which are positive charges, and to balance off the 3 protons, it has 3 electrons. We don't care about neutrons in this particular part of the lesson. So 3 and 3 are balanced. Now, lithium can lose an electron, and we're going to talk about that in the next few lessons as to why and how that can happen. But if lithium loses an electron, it's said to be ionized. It becomes an ion. And you see that lithium on the right has a different number of protons than electrons. It has 3 protons. It has only 2 electrons. That means the overall charge of that ion is positive because it has 1 more positive charge than negative charge. So ion in general means a different number of protons than electrons. The lithium atom on the left has 3 protons and 3 electrons, so the charge is balanced and the atom is electrically neutral. Electrically neutral means it doesn't have either a positive or a negative overall charge because they're balanced, positive and negative. The lithium atom on the right has 3 protons and 2 electrons and is a positively charged ion. Now, an ion can also have more electrons than protons, and that's called an anion. So an anion is an atom with more electrons than protons. So this fluorine atom is an example of an anion. It has 1 more electron than protons, so you can count the number of electrons, the negatives, and count the number of protons, the positive signs. An anion has a negative charge. So this grumpy guy is a negative ant. So just remember, negative ant, negative anion. They have a negative charge because they have more more electrons than protons. A cation is an atom that has more protons than electrons. It goes in the other direction. So here you see the lithium atom that we saw a couple of slides back. This lithium ion is an example of a cation. It has 3 protons and 2 electrons, which gives it a positive charge. So this dude is a positive cation. Just remember the positive cations are positively charged. Atomic mass unit. So the mass of each proton and neutron is 1 atomic mass unit, which is abbreviated AMU. It's not said AMU, it's just abbreviated AMU. So scientists just decided that they would define an atomic mass unit as the mass of a single proton or a single neutron because both a proton and a neutron have the same mass. An element's mass number tells us how many total protons and neutrons one atom of an isotope has. So different isotopes of the same element are going to have different mass numbers. So let's see an example. So one proton is one atomic mass unit, and one neutron is one atomic mass unit. An atomic mass unit, AMU, gives scientists a unit of measure for mass on the atomic scale. However, it is not practical for lab calculations simply because it's too small and too light for us to weigh on any kind of scale that we have. So let's learn how to read a periodic table here. You heard of some of these terms earlier, so now we're going to see what they mean. So atomic number, this is the number of protons that an element has. It is the number of protons that gives an element its identity. So the one for hydrogen, a hydrogen must have one proton. If the atom doesn't have one proton, it's simply not hydrogen. Helium must have two. So you'll find that number at the top of each entry of each element on the periodic table. The atomic number is also the number of electrons that an element has in its electrically neutral state. So when atoms are first created, when they're first born, they have exactly the same number of protons as electrons. They balance out each other. Electrically neutral means that the number of protons and electrons are the same. Atomic number is also called the Z number. I rarely use that term, but you will see it come up at times. So Z number is the same as atomic number. The atomic symbol is the abbreviation for the element that is used in chemical equations. Atomic symbols are often based on Greek or Latin names, so the letters don't always seem to match the element name. The atomic name, this is the name of the element. Atomic names can vary by language, however, the atomic symbols are universal across languages. So hydrogen, for example, has a different name in other languages, say Japanese or German. However, the letter H is used internationally to represent hydrogen so that chemists in one country can read the chemical equations of chemists in another country. Finally, the atomic mass. This is the average of the masses of all of the isotopes of an element. The atomic mass is the average mass of all isotopes of an element. This accounts for the decimal number. So if the majority of hydrogen atoms had a mass number, the majority of hydrogen isotopes had the mass number of 1, and occasionally you found an isotope that had a mass number of 2, in other words, it had a proton and a neutron attached to it, then you'd have an average that's slightly above 1. Example, if 50% of the isotopes of an element have a mass of 3 and 50% have a mass of 4, then the atomic mass of that element would be 3.5, halfway between 3 and 4. The rows in the periodic table are called periods. The columns are called groups. Oftentimes we will just refer to the rows as rows and to the columns as columns, but you should recognize the terms periods and groups. Rows are periods, columns are groups. So each period represents a new orbital. So now you're going to learn how to read the periodic table and how to diagram an atom based on the periodic table. So the first orbital represents the first row represents the first orbital. So hydrogen and helium have exactly one orbital. The second row represents the second orbital. So everything from lithium across to neon has 2 orbitals. It also has a first orbital, and it has a second orbital. When you go down to sodium, Na, all the way over to argon, Ar, those elements all have 3 orbitals. Now, when you go to the fourth row and below, it gets a little more complicated because you can see those light blue elements, the transition metals, they show up. And they add a number of extra orbitals. However, they are not valence orbitals. Only the, in the fourth row, for example, only K, Ca, Ga, Ge, As, Se, Br, and Kr, those are the only ones, the orbitals that are those are only ones that are part of the valence orbital. So there's also 8 elements in the valence orbital, or 8 electrons in the valence orbital, even when you get down into the transition metals. The 5th orbital represents the 5th row, and so on. Now each group, that is column, represents an additional valence electron. So the valence electrons we see, so the first column, which is hydrogen, lithium, sodium, potassium, on down, they all have 1 electron in their valence orbital, exactly 1. So for hydrogen, the valence orbital is the first orbital. It's the only orbital it has. So there's 1 electron in hydrogen's valence orbital. For lithium, it has 2 orbitals. So what that's saying is there's 1 electron in lithium's second orbital. That's its valence orbital. Sodium, Na, has 3 orbitals. It has 1 electron in its valence orbital, and so on down. If we move over to the next column, we have beryllium, magnesium, calcium, on down there. Each of those elements have 2 electrons in their valence orbital. So beryllium, Be, has 2 orbitals, and it has 2 electrons in its second orbital. Magnesium, Mg, has 3 orbitals. It also has 2 electrons in its outer orbital, which is its third orbital. Calcium has 4 orbitals. It has 2 electrons in its fourth orbital. Now we jump over the transition metals. We go over to where you see B, boron, and everything from boron on down, aluminum, gallium, indium. Those all have 3 electrons in their valence orbital. So the valence orbital for boron, B, is the second orbital. So boron has 3 electrons in its second orbital. Aluminum has 3 electrons in its third orbital, because that's the valence orbital for aluminum, and so on. And we can continue across. Everything from carbon on down in the 4A column, C, Si, Ge, all have 4 electrons in their outer orbital. 5, nitrogen, phosphorus, arsenic, they all have 5 electrons in their outer or valence orbital. Group 6A, oxygen, sulfur, selenium, they all have 6 electrons in their valence orbital. Group 7A, that's fluorine, chlorine, bromine, they all have 7 electrons in their outer orbital. And finally, group 8A are what are called the noble gases. They have 8 electrons. They have full second orbitals. That's why when you get to the end of a row and you've filled up all the, put all the electrons that you can into an orbital, then you have to go on to the next row and add a new orbital. So we'll talk about that more in just a moment. So we're going to build an atom, and we're going to build silicon. If you look at your periodic table, up in what you see here in the upper left is what you'll see on your periodic table. So silicon has an atomic number of 14. It has an atomic symbol of Si. It is called silicon, and it has an atomic mass of 28.09. Okay, so now we're going to go ahead and we write out a scoreboard. So it's number of protons, electrons, neutrons, orbitals, and valence electrons, electrons in the valence orbital. Down in that blank area on the lower right, you see that there is a rectangle that says protons and neutrons. That's where we're going to put our diagram. And that rectangle represents the nucleus. So you have protons and neutrons in the nucleus. I draw it as a rectangle so it won't be confused with the orbitals. Okay, so here we go. So you see silicon, it's in the third row there, and it's the 4th element from the left. I've closed the gap where the transition metals are just to save space. Okay, so here we go. Silicon has an atomic number of 14. So it has 14 protons and 14 electrons. So what we're going to do is fill in the scoreboard. If its atomic number is the number of protons, that's what defines silicon as being silicon. If it's electrically neutral, which all atoms are in the beginning, then it also has 14 electrons. So we can go ahead and fill in the first 2 places on our scoreboard. We can also place the 14 in the nucleus of the silicon down there, that rectangle. We're going to take the 14 electrons and set them off to the side for right now. So next we want to know the number of neutrons. So now we round the atomic mass to the nearest whole number. This is the mass of the most common isotope of silicon, which would be Si-28. If you have an atomic mass, it's whatever the closest whole number is, in this case 28, that's going to be the mass of the most common isotope. So we're going to go ahead and replace the 28.08 with just, 28.09 with just a 28. So watch what happens there. Watch what happens where the arrow is pointing. We replace it. So the most common isotope of silicon has a mass number of 28. That means it has a total of 28 protons and neutrons added together. So now we're ready to compute the number of neutrons. We do that by subtracting the atomic number from the mass number. So there's the mass number. It's the total number of protons and neutrons. Remember, each proton, each neutron has a mass of 1. So if your atom has and we don't count electrons. So if your atom has a mass of 28, it stands to reason that it must have a total of 28 protons and neutrons. And we know that 14 of those are protons. That's because of the atomic number, 14. That's how many protons. So if we take a total of 28 protons and neutrons added together, and we subtract the number of protons, which is 14, we get the number of neutrons, and that is also 14. So we can now place that in our scoreboard, right there where it says neutrons, and we can also place it in the nucleus of our atom. So now we have, our nucleus is complete. We have 14 protons and 14 neutrons. Because silicon is in the third period, that is the third row, it has 3 orbitals. So everything you see there being covered over in green has 3 orbitals. Everything in the third row has 3 orbitals. So we're going to go ahead and fill in the scoreboard with a 3, and now we're going to draw those 3 orbitals. So there's the first orbital, there's the second orbital, and there's the third orbital. Okay, all right, so we move on. So now we place the electrons. The first orbital gets 2 electrons, then it's full. The second orbital gets 8 electrons, then it's full. The final 4 electrons go in the outer orbital as they are spread out. So I'd like you to watch how I place these electrons. There's a reason for me doing it this way. So we're going to place the first electron right there. Now you don't have to place it on the bottom. I chose to do that. What you should pay attention to is how I spread the electrons out. So the second electron is going to go in the first orbital because it can only hold 2 electrons. You must fill the first orbital before you go on to the second orbital. You must fill the second orbital before you go on to the third orbital. So there we have our 2 electrons in the first orbital. That's all the electrons that the first orbital can hold. How do we know that? Because look at the first row on the periodic table. It only has 2 elements, hydrogen and helium. That tells you how many electrons the first orbital can hold. So now we put out the no vacancy sign for the first orbital. You cannot put any more electrons in the first orbital. Now we go on to the second orbital. We place the first electron there. Now we place the second electron away from it. Over on the left, we're now going to place the third electron on top and the fourth electron over to the right. So you see that the electrons are trying to spread themselves out. They don't want to be right next to each other if they don't have to be. But now we're at a point where there's only so many places to put these electrons. So the 5th electron in the second orbital is going to go join the first one. And so you see that they pair up down there in the second orbital. The next electron is going to go there, pair up. The next electron is going to go there and pair up. And the final electron for the second orbital is going to go there and pair up. So now the second orbital is full. It cannot hold more than 8 electrons. So that means for any additional electrons, we need to create a new orbital, and that will be the third orbital. So there's no vacancy in the second orbital. You cannot put any more electrons in there. So here we go. We're going to place the third orbital electrons the same way that we placed the second. So there's the first one on the bottom. The second one goes to the left. The third one goes on top, and the fourth one goes to the right. All right, so there it is. So now we look at how many valence electrons we have, and we see that we have 4 electrons in the valence orbital. The valence orbital for silicon is the third orbital, and it has 4 electrons. So we know that silicon has 4 valence electrons also because it is the 4th element in its row. So watch, we'll count over. So sodium is 1, magnesium is 2, aluminum is 3, and silicon is 4. You might just want to know how many valence electrons silicon has without going through this whole process of drawing a diagram. Okay, so that's how we do it. You can simply count from the left, and that's how many electrons will be in the outermost orbital. For silicon, it's the third orbital. So that's it for silicon. That's how you do a diagram of an atom using the periodic table. All right, and that ends our lesson on discovering the atom. So we're making some progress here, learning more about the atom and how to read the periodic table. It's not important that you memorize the periodic table. It is important that you know how to read it, to know what the rows mean and what the columns mean. All right, so that's it for this lesson. We'll see you on the next lesson.